So double click on Fluent, then here right click on Geometry, then go to Space Plane. So yesterday we worked on like external airflow, right? Today we will focus on internal airflow. I'll click on Z axis, so that I can visualize XY plane. Now click on New Sketch. Now I'll make a very simple design, okay? Now let's say if I choose line tool, let me make a CD nozzle kind of a structure. Okay, this is like a simple CD nozzle. Let me give it a dimensions now. I'll click the first line. It is 15 mm. I'll just keep it as 10. Now over here, this line, I'll keep it as 15. This one, I'll give it as 25. That's enough. Next is, I won't do the bottom half, okay? I won't be doing that. I'll be mirroring it in the next upcoming stages. So that's why I'll make a very long fluid domain. I'll choose line tool, select from the nozzle tip end, because this is inlet. These are converging wall, diverging wall. Now here is the exit now when the flow goes out. So I'll be making a large fluid domain. I'll go for a bit longer length. Bring it down to the axis, the center plane. Now connect it to the inlets line. Right? Now this is inlet. Bottom is symmetry. This is the wall. Here is the outer environment. Now I will just click on return to 3D mode so you get a visualizing like how exactly it is. Wherever the green section is there, the flow goes in that particular plane. The white and all is environment. I mean it's a cavity. It doesn't exist. This is enough. Now close it. Right click on mesh and click on edit. Now I'll click on Z axis. You will have to name the inlet, outlet and everything, right? So one thing I'll do, I'll just click on edge, zoom in, select this small line over here. That is the inlet, right? Click that, right click on it and name it. I'll name it as inlet. And now next is this section, these two wall. I'll select this and this line, right click and name it as wall. The bottom line, the whole bottom line will be treated as symmetry. Now the rest of the three lines, this one, this and over here, we will treat it as environment or outlet. Now just have a look, click on name selection here. Inlet is done, right? Wall, this is actually the throat, okay? The distance between symmetry and throat over here. That's the throat area and symmetry outlet. Now go to mesh. Mesh is around 42.5 mm. Okay, 42.6. So yeah, 42.5. Some random number. I'll assume it as 40 divided by 2. It is 20. I'll give it as 20 and click on generate mesh. I'll reduce it a bit more. I'll keep it as 10. I'll keep it as 4 and generate. It keeps on going small, right? I'll reduce a bit S size one more down, like I'll keep it as 2 mm and generate. I think this will be sufficient enough. You saw, right, how less we need to decrease the cell size for gaining accuracy. So right click on mesh and click on update, or you can directly click update here till you get a successful message at the bottom telling you're good to go. Now close it, right click on setup, click on edit, double precision, solver processor, keep it as 4 and start. So next thing you need to do is ignore everything on the top. Whatever you see over here, just make sure that it doesn't exist. So here, now I'll just click on the views on the top corner. Okay, just click on the views on the top and click on views again. Then click on symmetry and click on apply. So that now you can see second half of the nozzle came up, right? I will just repeat the process, okay? What you need to do, it will be like this, right? Click on views, views again, symmetry, apply, close. Now you see the complete seed nozzle being shown up. Now choose as density base, go to models, turn on the energy equation, viscous model, K epsilon, press OK, then go to materials, double click on air, ideal gas, create and close. Next go to boundary conditions, single click on inlet, and now what kind of inlet are you working on? Remember, this is a rocket engine nozzle, right? So this actually denotes that it is a pressure based inlet, whether if it's a turbo feed or pressure feed. So make sure in the type it is, click on inlet on a type, it is pressure inlet. There are many types of inlet. Inlet fan, intake fan, mass flow inlet, velocity inlet, pressure inlet. Choose pressure inlet. Then here gauge pressure and initial gauge pressure. These are the two things where it will ask. Now that is nothing but chamber pressure. Now let's say that at the chamber pressure it is like 100, at the bottom it will be 99. Now see over here, if I give 5 over here, it should be 4. Now let's say if I give a random number of 88, here I'm going to keep it as 87 or 85, something like that. That means, see, in the overall pressure within the chamber, theoretically we can suggest or tell that it is XYZ, like let's say 100 Pascal. But due to surface friction loss, air loss, and a certain turbulence, it won't be 100. It will be above 95%, under 99%. So let me give an example. I'll go with basic of 1 million pascals of pressure here as well, 99% of it. Then temperature of the overall airflow, I'll keep it to 1273 Kelvin. 1273 Kelvin. That means it is 1000 degrees Celsius. Then apply and close it. So it's done. Now click on outlet, edit. Now, at what environment are you working on? I mean, like where the flow is also, I mean, where is it going? That's the main thing. So I'll keep it at around sea level condition, like 101,325 pascals. Then apply and close. Right? That's it. That's more than enough. Go to methods. Make sure everything is in second order. Initialization and initialize. It's a 10-step process. It is calculated. Run calculation. I'll keep it as supersonic and calculate. So just make sure that all the graph lines what you see over here, it should decrease with respect to friction. Obviously, right? When it comes to wall friction, when as soon as the flow goes outside, surrounding air pressure tends to stop it. It acts like a pressure wall medium, right? It needs to pierce through it. So considering all those things, it should decrease. Now see, right, there is sudden turbulence rise up. That means the pressure is too much. It's a wrong simulation. I'll just show you. I just stop it in between. I'll go to graphics, contour. I'll just click on display. This is the pressure perspective. You see, right, there's no pressure. Why is that so? Because the pressure what we have given at the environment is too much for a very small design which also has extremely too much pressure. So it's all about varying the values. I'll click on inlet, edit. I will reduce the number a bit. Instead of 1 million, I'll give 100,000 pascals only. Apply and close. Now click on initialization, initialize. Any changes you do, make sure you initialize it and run calculate. Okay, so environmental pressure is too much. You see, right? Sea level like 101325. That's actually far more greater compared to the engine over here. So it should be far more greater. So let's say one thing. Let it be as it is. I'll go to outlet. I'll literally keep it as 0. Apply and close. Initialization and initialize. Calculate. So after each and every changes what you apply, you get an overall idea like how exactly these things work out. So it's good that all the lines are actually decreasing downwards. So now you can see the overall pressure coming up. So this is high pressure at the convergence section. So it drops and it converts to high velocity. I'll just change it in terms of velocity perspective. Now this is how it looks like. It is not enough. Now we need to increase the pressure because the red color thing must be throughout. So again, change the value. You go for more number. That means for the design it has good potential. We need to just vary with the values. So same thing happen when you work on the physical setup testing, right? You might have seen in the LinkedIn or on the WhatsApp, I keep on posting the flow videos of the engines what we test. So we do multiple inlet variations so that we can get a optimal thrust. It is not like you design something, you come up with some pressure value, and you expect the flow to be good. It won't happen like that. You need to wait for a longer time multiple calculations for like coming up with the different values, then you will get it. So let's give a try. Now you can see, right, the flow is actually kind of developing. So with respect to more pressure, now this is over expanded flow. Okay, you can see the Mach diamonds basically. I'll keep it as Mach number perspective. It tends to form diamond waves over here. This is over expanded. Pressure of the engine is lesser when compared to the environment. If it is under expanded, a huge plume will be formed up to denote it is far more greater. And if it's a perfect jet flow, the flow will be completely straight. So to do that, I'll just change the value one last time and we'll shift on to a different design. Now I'll give it as 4 million Pascal. At the bottom, 3.9 million Pascal. Initialization, initialize. Run calculation, calculate. Now stop it. Now you can see, right, the flow has been slightly extended. Mach number is 2.9, right? 2.9. So this is something good. Now this is enough. I'll go to path lines, select the whole thing, continuous, keep it as, I'll just keep it as 50, okay? And velocity, pulse. So you can see that the surrounding airflow gets attracted towards the low pressure zone when the flow has been generated. So red color flow is nothing but high speed velocity. High speed velocity means it is low pressure. So that's why you need to like you'll be able to figure out how exactly environment will behave with respect to flow going out. It will mix along with the flow. So this is enough. I'll just click on stop, close it. Now we will shift on to another design.